Is it better? A little bit? Like that? And yes, Vincenzo was right. The basic information in this lecture course is included in this textbook written with Maurice Clement. So in the first lecture, I will just give you the glimpse of basic properties of liquid crystals, the properties that made them the materials of choice in informational revolution that your parents actually experienced. You were kind of already born into it with all these devices that show information that you can carry around. So I'll be talking about different types of liquid crystals, including liotropics and thermotropics. Then I will talk about the basic physics of these materials, which is rooted in the anisotropy of each and every imaginable physical property of these materials. I'll be talking about surface anchoring. This is something new in addition to the isotropic part that we were exposed to in the previous lectures. Then I'll be talking about the specific elasticity associated with the orientational order. And we'll briefly discuss the effects such as Frederiks effect, which is at the heart of modern display applications of these materials. And it's important to, even if you're a theorist, it's important to understand how the people doing experiments get their images. And in the physics of liquid crystals and in many other branches, like in biology, for example, a lot of information is being obtained through polarizing microscopy observations. So I will give you the short introduction into that field, the optics of birefringent materials such as liquid crystals, and we'll discuss not only the regular polarizing microscopy, but also something a little bit more sophisticated that would allow you to create three-dimensional images of liquid crystals or biological samples. So in the second lecture tomorrow, I'll be talking about droplets of liquid crystals and topological defects. You would see that defect in a liquid crystal is not something kind of foreign, brought from outside and something that the liquid crystal waits to expel. In fact, in many equilibrium states, the equilibrium is achieved thanks to the topological defects. And we will discuss a especially clear example of that in liquid crystal droplets. In liquid crystal droplets, you can find exotic textures such as something that resemble Dirac monopole. You know that it's still something that people didn't find experimentally, at least not for sure, but you can always put a sample under the polarizing microscope and you can observe a structural analog of the Dirac monopole. I'll also discuss the peculiar elasticity of the lamellar phases. So lamellar phases are something that has not only orientational order, but also one-dimensional periodic order. And the elasticity of this media is very much different from what we know in solid crystals and from what we know in nematic liquid crystals. And finally, the lecture 3 will be a kind of more modern research, at least in our group, focused on dynamics of liquid crystals. I will cover the dynamics of colloidal particles in liquid crystals. This is something that is very far from equilibrium, being driven by the external electric field. You would see that even standard things such as Brownian motion of colloidal particle in the liquid crystal environment is totally different from what you would see in the isotropic fluid. And I will finish with the so-called living liquid crystals, which represent a kind of combination of the liquid crystal and active ingredients, active consumers of energy placed in the liquid crystal. So we should give a definition of the liquid crystal as something that has a long-range orientational order, but no or only partial long-range positional order. So the situation when we have no long-range positional order is called a nematic liquid crystal phase. The situation when we have only one-dimensional positional order is called Smectics, and two-dimensional positional order, but no positional order along the third dimension, is called the columnar phases. So this is a typical texture of the nematic liquid crystal that you would observe under the polarizing microscopes with two crossed polarizers. This thing is in constant motion simply because it has different molecular orientation at the top and at the bottom, and there is a small gradient of temperature that constantly drives the structure in the plane of observation. And you see these beautiful textures, that colors that I would hope to explain to you in details. These colors have nothing to do with any dyes present in the liquid crystal. You might see that the same point adopts different colors as time goes by. It's just the colors caused by effringence of the material and the way that you use two polarizers to observe the texture. So the goal is to give you a kind of intuitive understanding of the novelty in terms of physics and phenomena that liquid crystals bring to the area of soft matter. Because of that, I would necessarily skip some of the derivations and I wouldn't use that much the blackboard. But if you have a question, you can always challenge me to go to the blackboard or to ask me after the lecture or to read the notes. So this is the typical molecule of the liquid crystal that forms the nematic phase. It's called cyanobiphenyl, and this is the material that is a major ingredient in the development of liquid crystal displays, because with these materials that are robust in the sense of temperature range of existence and in terms of chemical stability, it was finally possible to create informational displays that are based on the dielectric anisotropy of the liquid crystal. So the material forms a liquid crystalline phase when you hit it above the melting point. So at very low temperatures, and in this case it's around 24 degrees centigrade and below, you have a normal molecular crystal. So these molecules possess not only some type of orientational order, not necessarily the way I show it here, it's a simplified picture. But what is important is that the centers of the molecules are sitting in the periodic lattice, and this lattice goes to infinity or to the end of your sample. Now, if you hit it, then at some point, the thermal fluctuations destroy the positional order. The molecules are starting to move around, but since they are still elongated, the shape doesn't change with temperature. You have a situation that it's preferable for them to remain parallel to each other. They're closely packed than to form an absolutely isotropic state. And this situation might exist within a certain temperature range, and this temperature range identifies the nematic phase. And we call it a thermotropic liquid crystal because it's caused by the changes in temperature. Now, the term nematic comes, in fact, from defects that this gentleman, Georges Friedel, observed under the microscope. So his microscope was with two crossed nickels, as shown here, although in this particular case it doesn't matter. So he just put the droplet of the nematic between two glass plates and then shear one plate with respect to the other. And he saw sudden appearance of these threads that would flow around, and he asked his niece how a thread would sound in Greek, and she said nema. Okay, he said let this type of material be called a nematic. So nema comes from the threads, and these threads are nothing else but the orientational analogs of dislocations. You know, dislocations, linear defects in metals and other crystals. So this is the orientational analog of dislocation, and the modern term for it is disclination. Yes? Actually, people, you know, melting of anything was always of great interest to people. And the first article that was actually published, I will give you the reference, was in 1861, I think, by a person who observed the melting of cholesterol derivatives and said, it's a strange material. It shows two-stage melting. First, I see some change into something fluid, but it shows brilliant colors, and then it goes into something that shows no colors at all and looks like water. So people were intrigued by just the melting processes, and Friedel was trying to understand what's between the crystalline state and the isotropic state. And he saw that, and he decided that this is a new type of the material. Now we know that the materials that form this nematic phase are formed either by strongly elongated molecules, rod-like molecules, or molecules that have the chemical anisotropy in a different direction, disc-like molecules. So both types of molecules produce uniaxial nematic-like crystal. What it means is that the molecules rotate around the axis, either the long axis or the short axis, and they are parallel to each other. So you have a system in which you have a preferred direction of orientation, and this direction is called the director, N. So, of course, thermal fluctuations make it that the individual axes of the molecules at any given time are slightly away from this overall direction of N. But again, this is the collective direction, and it specifies as the axis of symmetry of the Lie crystal in the so-called calometric or rod-like case and in the disc-like case. By looking at this picture, you might wonder what would happen if I will have something in between. Not exactly a disc, not exactly the rod, but some sort of a box. Then, in principle, there might be a biaxial nematic shown here. But an interesting thing that despite many theoretical models that would predict you nicely the existence of such a phase, experimentally it's not being observed, at least not in such a way that everyone would agree. This is a very active area of research, and people are debating about the very existence of this phase. Now you learned about chirality. And you probably know by now that in organic world there are chiral molecules, and the simplest example is the molecule in which this carbon atom is connected to 4 different groups around itself. So in liquid crystals, you often have a situation like this because organic molecules that people use in laboratory, especially at the in the early years of research, were derived from the organic world. For example, from cows, or from brains, or even from carrots. And this is one of those derivatives, derivative of cholesterol, that is chiral. And when you add such a type of molecule in the nematic Lie crystal, you have a dramatic transformation. Suddenly, the material that was not colorful before becomes very colorful. You see the kind of greenish bluish color here, then something close to it in the next domain, and there are some bright domain walls separating these regions. The colors do not come from any pigments or dyes. So who can tell me where the colors come from? Exactly. So it turns out that these chiral interactions, they're not that strong, but they're still capable of changing the structure. And since they are not that strong, the period of this structure is not, the period of the twist is not comparable to the molecular scale. It is much larger. And it's on the order of few fractions of a micrometer. It's just an experimental fact. And because of that, you have a Bragg reflection on the stack of periodically changing molecules in space, and this gives rise to the colors. Now, it's also important when you're dealing with soft matter to understand the connection between the property of the material and the chemical structure. So on the top is just 2 very similar molecules. One is pentyl cyanobiphenyl, and another molecule is just the same thing, but in the tail, you just remove one of the segments and put it to the side in the chiral fashion. And suddenly, you have a cholesteric out of the nematic. So the question is, what would happen if I would just create a dimer out of these cyanobiphenyl molecules? So the question might be kind of futile and not very inspiring, because the answer looks to be very simple. It depends on the number of the links in this bridge. If it's even, then the conformation will be most probably of the trans type. It means that the molecule will look like a rod. But if it's an odd number of links, then you would expect something that has a bent shape. And if it's the even number of links, you would expect that this material would behave totally as a nematic, like crystal, just orientation. All the molecules will be aligned along the same direction. But if it's a bent shape, then you're actually not so sure. It might be a nematic. Maybe the desire to be parallel to each other will just make these molecules not being bent at all. But it's clear that if you're trying to create something like a constant bend, and I think that you were dealing with this type of a problem in 2 dimensions during the first week of the school, so you would see that it's impossible to provide the bend that would satisfy the desire of the bend-shaped molecules to bend. So it's impossible to create the bend that is constant in the entire 2-dimensional plane. But if you think kind of outside the box, if you think, what if I could go into the 3rd dimension and create an imaginary cylindrical body, and now you wrap these bend-shaped molecules around the surface of the cylinder and then go along the axis of the cylinder, you would realize that it's possible. You can just add all this heliconical structure or threads, one to the next, and you would obtain the new phase that is called the twistband nematic phase that was predicted a very long time ago and was kind of featured in a number of theoretical works. But amazingly, till only 2 or even less years ago, it wasn't observed experimentally. The experiments came actually from the University of Colorado and from Kent State University independently. This is a typical transmission electron microscopy texture of this twistband nematic phase. It shows you the series of stripes with a period of only 8 nanometers. And this period doesn't match the lengths of the molecules, the widths of the molecules. It's just something very strange and very small. So one of the explanation of these lines is that you have the twistband structure, and in the who knows how the imaging and transmission electron microscopy works? Okay, 1, 2 out of maybe 60. So typically what you do, you have to prepare the sample. So you place the sample between 2 metal blocks, and then you quickly quench it to the temperatures at which everything glassifies. Everything becomes kind of frozen and amorphous. Then you pull open these 2 metallic blocks, and this ruptures the specimen. And then you have 2 surfaces. You deposit heavy metals. You create a replica of the profile. And then this replica of heavy metal, being reinforced also by some carbon film, you place under the beam of electrons, and they provide you the luxury of resolution with few nanometers, as you might see here. So it is natural to speculate that, okay, when I break open the thing, my surface of fracture is the surface in which the density of molecules is the smallest, or in which the molecules are not crossing perpendicularly. And that would be the fracture that is parallel to the heliconical axis. And then if I deposit something, of course, these valleys will collect all the heavy metals, and I would see this periodicity under the transmission electron microscope. But that kind of doesn't give you a satisfaction of being absolutely sure that what you are seeing is exactly the twistband nematic. So you need some additional experiments to do, because, for example, this periodic layering might be simply a smectic, in which you have the 1-dimensional periodic order, and the replica just picks it up. So you do X-ray, and the X-ray tells you, no, there is no density variation. It's just all homogeneous. So then you work more with the specimens, and you are trying to reach a situation when the fracture is not parallel to the heliconical axis, but tilted. And this is the image that was taken in a very long time ago, in '68, by Yves Bouligan, who was the first to establish that chromatin in chromosomes of many species is forming a cholestatic liquid crystal. So people didn't believe him. What he did, he just showed this drawing in which he showed the cholestatic. You see this helicoidal structure, and then when you cross it under the certain angle, what you would see that the director is periodically bending and forms these arches, and these arches are called the Boulder arches. So it turns out that if now instead of the cholestatic, you're dealing with the twistband nematic, then the difference is that in the cholestatic you have a right angle helicoid. The axis is vertical. All the molecules are rotating, remaining perpendicular to the axis. Here, the axis is vertical, but the molecules are rotating with some non-90 degrees twist. And that brings all the difference in the cross-sectional views of the microscope. You see that these arches are now not symmetric or not well developed, and this is precisely what the new phase shows under the microscope. Either the alternating arches of wider and narrow type, or underdeveloped just arches. So it's amazing that for more than 100 years, people were dealing with nematics and cholestatics, and only recently it was realized that the liquid crystals lived in a much more dimensional, I would say, world in which the nematics and cholestatics are just the two end points, because this structure in between is described by this general formula in which theta is different from pi over 2 and 0. If theta naught is 0, that's a nematic. If it's pi over 2, it's a normal cholestatic. I put the blue line as the dividing line. Who can tell me why did I do so? What is the difference between the two left structures and one structure on the right? Order parameter, each and every liquid crystal has its own kind of order parameter. No, this is also periodic. It has the pitch, and that pitch is 8 nanometers, by the way. This pitch is 0.5 micrometers, so it's not to scale. But there is a fundamental difference. Layered? No, all of them have no periodic variation of density. You take X-ray of any of those three, it will show you nothing of interest. Well, yeah, you can say, but it's not actually 0. If you average it, you would get no orientation parallel to the Z. All the molecules are parallel to X, Y. So X and Y components are non-zero. Z component is 0. So it's not that. You have to be, what? Band? Yeah, there is a band, but so there is a twist here. So here there is a twist. And that's it. No band. And here there is a band and a twist. Right. And here there is no band, no twist.
This guy has a mirror plane.
Yes. So, and what I was actually expecting to hear was that you already saw. You see, the cholestatics are formed by chiral molecules. And this molecule that forms the twist band is what? Is it chiral or not? It is not chiral. So it's amazing. You have the chiral symmetry breaking in this simple organic material when people are chasing this phenomena in who knows what high energy physics and elementary particles. You have it right there. You have it under your nose. You can put it under the microscope and observe that the structure is chiral, in fact. And of course, if you prepare the sample, then the probability of finding right and left domains is roughly the same. Okay, Leo actually already introduced the Smectics to you. This is why I use the term and already kind of contrasted it to the nematics. But this is what it is. It's a structure in which, in addition to this orientational order, you have a one-dimensional periodicity in the structure in terms of the density. And you can easily verify that by X-ray. You would see the reflexes that would correspond to the period of the structure, which is typically on the order of the molecular lengths, depending on the conformation, or sometimes on the desire of the two neighboring molecules to form a dimer. It might be a little bit more, like 1.4 lengths of the molecule, but roughly speaking, it's a few nanometers thing. So it's amazing that the structure that you just saw of one-dimensional periodic ordering of molecules that are all looking into the same direction was correctly predicted or correctly stated well before the X-ray was even invented. In 1910, Georges Friedel, the same person that gave the name to nematics, and by the way, he gave the name to smectics as well, observed under the microscope some strange geometrical figures like this one with ellipse, and then some line that probably resembles a hyperbola, and then again some elliptical shapes. And he said, this material must be comprised of fluid layers stacked on top of each other, and these layers must be equidistant. So that was an amazing prediction if you think that it was made about the structure of matter at the scale of nanometers from observing the stuff under the optical microscope. What is the smallest thing that you can observe under the optical microscope? I mean, distinguish. 300 nanometers. Who gives more credit to optical microscopy? This is right, but this is just the regular optical microscope.
Yeah,
Exactly. Who got the Nobel Prize? Very easy. Hell, you know, H-E-L-L. Stephen Hell. So what's the record now?
I think 1
Yeah, now you are ahead of me. I'm not sure. It's on the order of 10. The last I saw was 20 nanometers. But anyway, so at that time, nothing of this was, Mr. or Dr. Hell was not even born. And still, you know, it's an amazing thing. People simply knew mathematics. People knew geometry. Once they saw the elliptical things, they immediately concluded how the structure is organized at the molecular level. We will talk about this later because these things are the so-called focal conic domains, and each and every one must know about them, and I will make sure that you do. Okay, so there are many other smectics. In the smectic A, the molecules are perpendicular to the plane of the layer, but you can have a situation when it's tilted. You can also have the situation when the molecules are chiral, so they form nothing else but the heliconical structure. This structure is different from the nematic twistband phase only because it shows layering. In the nematic twistband, there is no layering. There are even more sophisticated things, with especially when the molecules are chiral. Imagine that the molecule is chiral but still wants to form a smectic. And so if you think about so that would mean that at some point the structure would like to twist. But if you take if you take a notebook, something like that, and if you try to twist it, you would realize that it's very hard to do because the pages would like to be parallel to each other and would like to keep their thickness, their equidistance. So it's impossible. Twist and layering are typically incompatible. And so it was a great discovery made first theoretically by Lubansky and his student Ren, and then experimentally by Pinda, Goodby, and others, that you might have a compromise. It's the analog of the Abrikosov phase. Who knows about the Abrikosov phase? No one. Wonderful. So forget about the analogy. It's not the analog of anything that you don't know. Yeah, but still they don't know what the Abrikosov phase. So anyway, it's a cool thing when you have a superconductor and you have the magnetic field acting on it, and it transforms the superconductivity into the normal metal. But okay, it's something that we're not obliged to know. Anyway, so what happens here is that the system finds a compromise between the twisting and layering by introducing a lattice of screw dislocations that penetrate the bulk and allow the material to be within this range a smectic, just a normal smectic. But then, you know, the next block dramatically twists with respect to the previous one, and you have this beautiful phase-supported, defect-supported new phase in the Lick crystals.
What's the length?
LD, it's about 100 nanometers. So now we are coming back to the scheme, here I told you that it's the temperature that controls the phase transition. And in fact, this is why we call most of the Lick crystals, especially those that we use in the displays, we call them thermotropic Lick crystals. There are also so-called Liotropic Lick crystals, and they are a beautiful illustration of the theoretical model that was proposed by Onsager in 1949, how two different types of entropy might compete with each other and establish something new in the condensed matter. So he was considering the following situation. Imagine, a tank with water, and I throw some long rods in that tank. So by entropy reasons, the rods should find all the corners of this tank and explore the entire volume available to them, so they just move around. And they also should be aligned in different directions to maximize the orientational entropy. But now imagine that I find the source of these rods, and I just throw more and more of those rods inside the tank. And at some stage, I would observe some crowding effect. So here, this blue rod would like to move upwards, but there are these two red rods that just prevent this motion. So Onsager thought that if he sacrifices the need for the molecules to be oriented into the different directions, then he could ask these red molecules to realign so that they open the passage for the blue molecule, and the blue molecule can explore the translational degrees of freedom. And so he realized that at some critical concentration, the entire material should realign along one particular direction so that the molecules can still continue to move around freely. And that was a wonderful prediction. And in fact, he was inspired by the experimentalists Bernal and his colleague Fankuchen, who observed the water solutions of tobacco mosaic virus. They found out that at certain high concentrations of this tobacco mosaic virus, they form bifringent elongated droplets. And the viruses inside these droplets that are kind of rod-like entities, they are apparently oriented from one pole to the other. They couldn't see each and every individual rod-like tobacco mosaic virus individually because they were still too small for the instrumentation in 1941, but they correctly assumed that it must be the orientational order, and maybe some smecticity, as you might see here in the original picture, that is aligned along the long axis of the tectoid. So, as you might imagine, since the phase of orientationally ordered rods, which is, by the way, nothing else but a nematic, is formed as a result of competition between two types of entropy, orientational and positional, and orientational lost the battle. The resultant phase diagram should not depend on temperature. So all it depends on is the concentration in the Onsager model. These are the molecules besides the tobacco mosaic virus, which are just simply rigid rods. These are the molecules that in principle form something that resembles the elongated rods. But you need many molecules of this type, of a surfactant type or phospholipid type, to create first spheres and then elongated needles that might form a nematic phase, or if they are almost infinitely long, they might form a columnar phase. I would like to also introduce you a very special type of the Lick crystal, so-called chromonic Lick crystal, which is, as you would probably hear from Noel Clarke, are very similar to the DNA arrangements in water solutions. So we are dealing here is molecules that are kind of flat, rigid core, and no aliphatic tails, but just some ionic groups or ionizable groups at the periphery. So when you throw this thing in water, what happens is that the molecules would prefer to hide their faces away from water by stacking on top of each other. It's like hydrophobicity of the polyaromatic core that leads to this arrangement. And so if you have enough of molecules of this type, they would form aggregates that are rod-like and that might be very long. Yes? No, this is the disk. So this is as close as I can image or draw a disk. A disk. A coin. Do you have a coin in your pocket? Just imagine you have many coins in your pocket and just put them on top of each other. These coins are what? Yeah, but we are talking physics, so this is this is coin. It's almost, yeah, it's flat. It's flat. It's you know, for all intents and purposes, for this model, it's flat. Of course, when they pack, they are slightly, you know, rotated with respect to each other.
Yes, I never understood the word. Why is it just this odd? What is the reason to make a distinction?
Because if they would be flowing in the isotopic fluid as in discotic, in discotic nematic, what you would have, you have a lot of penalty. So this is the one disk, this is the other disk. Yeah, you're right, they might have some slight interest. But the point is that this is water, and this is water. And this surface and this surface are not happy with water being in proximity. So they are much more happier to see their neighbor, polyaromatic organic material, at the surface. This is why they form aggregate that would grow in principle to infinity if you provide a lot of material. And this formula, by the way, is an expression for the typical length of the aggregate in isotropic solution. Yes?
There's a distinction that in discotics, they don't have any energetic stickiness.
Exactly.
They just form because of entropy.
Yes.
Okay, because they're
Right.
While here there's an energetic enthalpy component.
Right. And this, you know, red regions are just charged regions. They can be negative or they can be positive. And these are highly hydrophilic. So by stacking the molecules this way, what I also create, I create the surface that is very hydrophilic. And it's very nice for the aggregates to be in water when their surfaces are hydrophilic. It's exactly the same thing that you have with surfactants. Surfactants for micelles, in order to put the hydrophilic heads at the periphery and hide the hydrophobic aliphatic tails inside so that they don't perturb this network of hydrogen bonds in water. Yes? Yes, so the convention here is the same as on the top left corner. So you know about electric double layers, do you? So you have a charged surface. So okay, let's just, so I'm assembling this aggregate, right? So I have the groups, and now the axis of the aggregate is horizontal. So you have negative charges, and the positive charges are somewhere else because they, you know, are dissociated, but there is an colonic attraction between positive charges and negative charges. So the balance of this colonic attraction and the entropic desire of the positive ions to wander around leads to the establishment of the electric double layer with the thickness that we call the Debye screening length. In this case, it's few nanometers, comparable to the diameter of the molecules involved. Any other questions? Okay. So again, this, as I mentioned, Noel Clarke will be probably talking about the chromonic arrangement of DNA molecules, nucleotides. It's a very similar thing. For example, the aggregation type in chromonics is very similar to what you see for the nucleotides in the duplexes of DNA, and even the charge per unit length of DNA and chromonic aggregates is in most of the cases the same things. It's about 6 maximum charges, 6 electron charges per 1 nanometer of the length of this cylindrical body.
For those type of liquid crystal, what determines basically the maximum length that they can achieve?
Yeah, it's a good question. So in the isotropic phase, it's this formula. What you take the stickiness, the desire them to stick together, and then again the entropy, that they would like to go as far away from each other as possible. And the balance of this enthalpy and entropy leads to the very simple estimate of the length, which is the square root of concentration of these molecules. And then on the top, it's the energy of the stickiness.
Basically, that can be tuned by the ion crystal.
Of course, yeah. It's an amazing thing. You take the isotropic solution of the chromonic, you salt it a little bit, and boom, it goes into the nematic phase. It's like nematic margarita if you put just so. It's a very nice illustration of what you just said. So I would like to explain you this diagram, which explains the basic types of liquid crystals we might have. So in the center, it's the thermotropic liquid crystals from the display applications and many other things. So the concentration here is what? It's like 100%. The entire droplet or piece is filled with the same molecules. They're closely packed, so there is no solvent here. It's just the same material everywhere. The molecules are closely packed, so it's this picture is probably not producing the degree of packing very well, because it shows some huge gaps. But the only thing you can do to this material to make it a nematic or other type of the liquid crystal, or to melt it into the isotopic phase, is to change the temperature. That's it. Now in the Onsager system, temperature is not relevant. All you do is you have a solvent, you have the foreign entities that are anisometric, long rods, or long disks, or I mean wide disks, thin disks. And if you change the concentration of the things, you would have the change in the phase state. And the chromonics are kind of LC squared. LC squared means that you have 2 handles to control their phase behavior. You can change the concentration, but you can also change temperature. And this is the typical phase diagram that shows the nematic domain that is sensitive to the concentration of the molecules and to the temperature. So it leads to very interesting physics in these materials, and physics that resembles, as I said, many things that are observed in biological world. This is just a movie that shows you how dramatically different the droplets of liquid crystals might be as compared to the droplets of isotropic phases. This is the nucleation of the chromonic liquid crystal from the isotropic melt. So you change the temperature a little bit, cool the sample down, and the material, it starts to nucleate as little pieces. Then these pieces elongate into kind of whips, and then they realize that the best way for them to be deformed is to form tori. And so all these things are little tori, donuts, if you wish. And the reason is that the material in this concentration and at this temperature wants to form a columnar phase, and columnar phase is something that, as I said, had 2-dimensional order in one direction and fluid order in the other direction. So this direction has no well-defined periodicity, but in this XY direction you have hexagonal packing. So what happens is that these cylindrical things, they can be very, very easily bent, but there is no other deformation that they can sustain. This is why they cannot form droplets of the normal shape with the spherical interface, because then you simply don't know how to put this cylindrical bodies inside, you can start doing something like that, but there will be a huge defect in the center. So the material simply forms tori, and this is how the columnar aggregates are packed within this body. Any questions? So should we have a break then? Okay. No, you can erase from the.
I think I'm missing some bits of the last picture. Like, what are the aggregates made of? They're
Molecules. Molecules are like disks, little disks.
Alright.
And these disks, when they find each other, they would like to
stick together.
right.
Alright. So because like the end of the first is the end of the one.
No, not like this. Like points, like this. Not like this.
Okay,
Not the chain, but the columns.
okay, they pile up.
Pile up. Right.
But what were we seeing in the image? They were like the borders of the coins, or?
No, they remember this is 1 nanometer.
I see.
You don't see it, but you see the kind of the condensed phase that is formed by these cylindrical aggregates. They are
Okay, so
packed
I see
in
that.
hexagonal lattice.
All right.
So these flexible cylindrical things are just packed, like my fingers are packed now. And then
Okay,
I'm asking, how can I deform that?
All right.
It's bent.
Okay, so they like I'm seeing a ring and made of lots of bright spots, but I cannot distinguish them, and that's what I put on the box.
Yeah.
Right. That's why you also need that consent, right? Because that's
Because it's a pure
Yeah.
band. So
okay, and that's not,
yeah, DNA packed the same way, because DNA is also this rods, right? So the easiest thing for them to pack is through rods.
Okay.
Think of them as very long.
Yes. In theory, it's infinitely long. Because if they would be not infinitely long, then it would be like a nematic.
So that's why they.
Yeah, they don't want to have this ends of the column. When they wrap into the tori, you don't have this last molecule exposing phase towards water.
I can do like. Wait. Just.
I'm just thinking about us like that.
I really would like.
Make sure your heels up, right?
What by going to the gym every day?
Yeah, right. Just,
Jumping off the climbing board.
You probably have been better by now.
Do extra biking.
Okay, I will continue. So I mentioned that when the molecules are oriented along the same direction called the director, then all the physical properties become anisotropic. That means that the physical properties such as dielectric permittivity would depend on the direction along which you measure it. For example, you are measuring you're taking the condenser and you're measuring the capacitance of that condenser. If it's filled with a liquid crystal in one geometry or in the other geometry, the result would be different. And this is the tensor of the dielectric permittivity. If you measure epsilon along the direction perpendicular to the director, either x or y, you would get the same number. Because the structure is axially symmetric. But if you measure it parallel to the director, then you would get a number that is generally different from the two others. The anisotropy is significant. For example, when it comes to the relative dielectric permittivities, you might see that delta epsilon is 10, very much comparable with the epsilon along the director. The same goes with birefringence. The difference in the refractive indices measured for light propagating with polarization parallel to the optic axis, which is the director, is 1.7. For the polarization perpendicular to the director, it's 1.5. So you get some 15% of the absolute value of the refractive indices. And because of this, the liquid crystals are extremely sensitive to the external fields. You take a magnetic field or you take the electric field, you apply it to the liquid crystal. The liquid crystal tries to realign in order to minimize the energy of interaction between the anisotropic, let's say, dielectric permittivity and the direction of the electric field. So this is the example of the classic effect that we call Frederiks effect, how the liquid crystal reacts to the application of the external field. Imagine you have the liquid crystal between two glass plates, and these plates impose tangential orientation of the director. And so the director will be happy in this state if there are no external field. But if you apply the electric field, for example, along the vertical direction here, you can simply do it by coating the glass plates with indium tin oxide, which is a transparent electrode on top and on the bottom. So you attach it to the generator, you would get the electric field. The molecules, if they have epsilon parallel being larger than epsilon perpendicular, would try to realign to be parallel to the electric field. And the only thing that is not happy about it is this surface interaction at the boundary at the top and the bottom, because that interaction is such that the molecules are preferably parallel to the boundary. So the effect was discovered by Vsevolod Frederiks, who did many other things at the time. He did cosmology and made a number of interesting observations there. He did a very simple experiment. He just took a flat glass plate and a lens, a glass lens, and he put one on top of the other, and he filled the space with the liquid crystal, and then he applied electric field. And by observing the interference pattern, he was able to deduce that there is a realignment of the optic axis of the material, and the critical field at which this realignment occurs being multiplied by the local thickness of the space between the two glass pieces is a constant. So now we call this the Frederiks effect, and its electric field version is being used in the Lake crystal displays. This is the person who was the first successfully applying the Frederiks transition to the commercially viable product. This is the grandfather of all these iPods and flat panel TV screens produced in Kent, Ohio. This is the principle. By applying electric field, you change the orientation of molecules, so the polarized light comes through the cell with different polarization properties, and if you arrange things properly, you would see either a beam that goes through or the beam that is totally prevented from going through by the second polarizer that is placed after the Lake crystal cell. So as I said, this is the same principle that is used in all the modern Lake crystal displays. So the Lake crystal is acting as the decider how much light will go through. And then you have the panel of color filters. And depending on which color filter gets more light, you would have one color or the other. Very simple principle. And of course, the industry is booming. Last year, there were 3.5 billion LCD panels sold worldwide. How many people do we have on this earth? How many? 7. So almost one per couple. So okay, let's think about the mathematical description of the Lake crystal. So as I said, the ground state is the state in which the molecules are orientationally ordered. They look along the same direction called the director. Imagine now I want to make a deformation, like I want to splay them like my fingers. Obviously, I should perform some work for that because I'm doing something against the will of the molecules. And obviously, there will be some elastic constant, let's call it K, and there should be some gradients of the director field or changes in the orientation of the director in space. So there should be some gradients of the director. Now, I am not showing you the linear dependency of the free energy density on the gradient of the director, because I'm thinking that if I want to move the director to the right, let's say a positive gradient, and then if I want to distort it to the left, it's an opposite sign of the gradient, but the energy should be the same. So the linear terms should not contribute. This is why I have this quantity as squared. And then I think, okay, n is just the direction. As a vector, it doesn't have the amplitude that is of any meaning. The amplitude of this vector is always 1. It just shows you the direction of the orientation. X, the space coordinate, is of the dimensionality of length. So my thinking at this moment is that most probably the estimate for the free energy density is K divided by the scale of deformations L, the length of this or the diameter of this splayed body. So, but this is the free energy density. If I'm interested in the total elastic energy of a piece of body that is distorted, then I have to take the volume integral, and on the dimensional grounds, I have to multiply this by L cubed, and so the result will be that the energy scales linearly with the size of the deformed body. And this is an absolutely important thing to remember when you're dealing with Lake crystals, because it's different from you have in solids, and it leads to some very counterintuitive results. So another thing is that obviously Lake crystals are always bounded. There are some surfaces, some containers, because if I don't have a container, the Lake crystal will just flow away. It's a fluid. And at this boundary, the anisotropy of molecular interactions that is responsible for the orientational order in the bulk is also set in some preferential alignment. In this particular case, I show that the molecules are tangential to the surface. If I need to change that orientation, again, I have to perform some work. I need some external torque that would come and change the orientation of the director at the surface. And if I think about the work that this torque needs to perform, then I would reason that, okay, per unit area, it should be some material constant that characterizes this pair of the Lake crystal and the substrate, and multiply by the angle of distortion squared. Again, I cannot just put theta because theta and minus theta are the same thing in terms of work I need to perform. So I need to square it. And then the surface energy per area of extension L should be something like WL squared. Now, if you think about the dimensionalities, yeah, this just shows if the torque is not there, the molecules come back to the original equilibrium state. If you think about the dimensionalities of these things, you would, of these and these things, they should be of the same dimension, joules. You would realize that the quantity K over W has the dimension of length. So what is your guess about the length value that we should find in the nematics? So this is the material. It has bulk properties, elasticity, surface properties, anchoring. And the two constants being divided one by the other give you the length. What should be that length? Huh? Yeah, that's true, but give me some number. Just a micron. How does micron come into play? Okay, it's a good thing actually that you don't know, because you know, many people say, hey, look, K, okay, let's just see. So how can we estimate K? So what is K? K is the measure of elastic interactions that are possible only if the material is in the nematic phase. If you melt it in the isotropic phase, K should disappear, right? So my guess would be that in orders of magnitude, K has the dimensionality of, by the way, of force, right? Because energy is force by some length, so K is of dimensionality force. So how can I get force out of the liquid crystal existence? First, I think, okay, there should be some energy of anisotropic interactions, and this energy can be estimated as the Boltzmann energy that corresponds to the temperature at which the material melts. So this T and I is the melting temperature of the material. How big is this temperature? Let's suppose it's around 100 degrees centigrade, right? So somewhat higher than the room temperature. And then there should be some lengths. So in the liquid crystal, what kind of lengths do I have? Size of the molecule. Is it written there? No. Good job. So it's the size of the molecule. So I take 1 nanometer or 1.5 or 2 nanometers, and I divide one by the other, and I get 5 piconewtons. So there are people in this room that did a great job and hard job by measuring these things, and they would testify that no matter what they do, they would get quantity either the same as shown here, or like 8 times smaller or 8 times larger. But this is a correct estimate. Now, surface tension. I'm not talking about the anisotropic part of the surface tension, not about the anchoring, but surface tension. Many people would show you the theories that would tell, okay, surface tension is basically the Boltzmann temperature divided by the characteristic molecular scale squared, because that's how you get the right dimensionality. And if you do that, you would get something like 10 to the minus 2 joule per meter square. And it's more or less correct. But it turns out that when it comes to W, the anisotropic part of the surface tension, it's the situation when the intuition totally fails you. Except if you're Lisa, then she correctly stated that the ratio of K over W is about 1 micrometer. But it comes from the experimental findings. So people actually do measure how much work does it take to deviate the director from the preferred orientation at the substrate, and they found that depending on the materials, it ranges from 10 to the minus 3 to 10 to the minus 6 in System International. And then if you divide the thing on the top by the thing at the bottom, you would get 1 micrometer plus minus a few orders of magnitude. But it's just simply because there are so many different materials. And the most important part here is just to remember that it's not nearly close to the molecular scale A. So again, be careful about the intuition. Sometimes it can mislead you. But if you do the experimental measurements, then you will find solid ground. So we will come back to this amazing thing that this thing is about 1 micrometer, and this is, by the way, the scale of colloidal physics, right? Colloids are things that are happening at the scale of micrometer and below. So this brings some interesting results from the physics when you mix liquid crystals and colloids together. So now let's talk about more precise description of elasticity. So we were talking about some twist deformations, some bend deformations, and you apparently didn't have a clear clue what exactly the difference between splay, bend, and twist. So that was the situation for most of the 20th century for all the people until Ozin in 33 wrote the preliminary draft of the elastic theory, and then Frank finished it in 58. So the idea is the following. You have the uniform ground state, and then some external forces like electric field or surface boundary conditions want the director to be deformed. Again, what is that work that needs to be spent over the system to get this deformation? You can reason as a normal theorist would that let's make an expansion. So I don't know the energy density, but I know that I can expand it in terms of the small deformations, which are nothing else but the gradients of the director field with respect to the special coordinates. There will be some linear term, maybe not, quadratic, and then I go up and up with also maybe the second derivatives and the third derivatives. And then I need to simply remove from this expansion the terms that are not relevant. So the terms that are not relevant are apparently this F naught. I don't know, it's just sitting there of no interest to me. It doesn't depend on the director. The linear terms should not be there because if I have splayed to positive and negative sides, it's all the same. So most probably I will start with these terms. But then these terms should satisfy a couple of additional constraints. First, of course, that the gradients are always small. That means smaller than 1 over the molecular scale. N and minus n in my final expression for the free energy density should not be distinguishable from each other. Remember, I showed you the molecules, although some of them were having some dipole moments, the directionality of those dipole moments were arbitrary. I mean, to left and to the right was the same probability. So the expression should satisfy that condition that the central inversion is preserved about any points. And if you rotate the deformed system around the local n, you should not change the free energy density. So you can do a very kind of detailed consideration of all these conditions, but we are not having time for that. Yes. No, for biaxials, it's a little bit more complicated because, for example, you don't have the invariance around any rotation around n because you have the secondary director. But don't worry, they experimentally kind of apparently do not exist, so biaxial numerics. What we would just do, a very simple thing. So apparently these derivatives can be represented in the coordinate independent way, and that means that I need to deal with things like divergence and curl of the vector field n. And if I look at the divergence, it's kind of a good thing. It's a scalar to begin with, and that's nice because the energy is scalar. It doesn't have any directionality. So divergence is good, but if I change the sign of n to minus n, divergence changes the sign, so it doesn't satisfy this condition. But divergence square of n is good because no matter what sign is here, the divergence square is still of the same sign. So n curl n is an interesting thing. It satisfies everything except that it does not satisfy the central inversion. But again, if I take the square of the thing, then it will be a very good candidate. And then I would consider curl n. It's also a good candidate. So these three are a very good thing to be in the free energy expansion. And then I just make use of the identity that curl n is nothing else but the sum of vector and scalar product of n and curl n. And I just write down, just from the sky, the expression that I think should be the free energy density. for the nematic Lich crystal. And then I take a textbook and I verify this is precisely what is derived in the textbook. So, and if you want to do Lich crystal physics, you have to know this expression by heart. In the present form, it was, again, written by Frank. This is why we call this elastic constants by Frank's name. It's Frank elastic constants K1, corresponding to splay, K2 twist, K3 bend. But the expression is called Frank-Ozin expression. This is why I have the subscript here. So this is how these three independent and different types of distortions look like in space. This is splay. It's literally what I show you with my fingers. This is splay of director lines. It can be two-dimensional. In that case, the divergence is 1/r. Or it can be three-dimensional around a single point. In that case, it's 2/r, the density of splay. Twist. It's just what I'm doing with my hands. You go along the single direction in space, and the director rotates, and it's like in cholesteric. And bend, I take the rod or the director line, and I do like this. Not very strongly, because the gradient should not be higher than 1/molecular scale. Okay, so this is a geometrical interpretation of the deformations. Now let's see how this anisotropic elasticity works in the simplest problem possible. Imagine that you have a film, spreading film on the surface of glycerol or water, for example. The crystal would spread, and if you have the proper conditions, it would wet the film, and you would have a relatively flat piece of a Lich crystal. Now, this Lich crystal has a boundary beneath of it being glycerol or water, and you would expect that the surface easy axis, the orientation that is imposed by the interaction between the molecules here, would be something, and that something experimentally is tangential. So the molecules of most of Lich crystals prefer to be parallel to the surface of water or glycerol, and this would be air, for example, free surface. And again, experiments tell you that typically the molecules of Lich crystals prefer to be perpendicular to this interface. So now I know that there are two boundary conditions, and I'm interested to know what would be the director field as the function of z. I'm going from one point to another. I want to know what is the particular director tilt, let's say in this point, in this point, in this point. Why I'm interested in that? For example, I am developing the new type of a display, and the birefringence, effective birefringence, would depend on the director orientation, because director is nothing else but the optic axis. So I need to know that. So what do? I first make an assumption. I assume that my problem is restricted to this plane, that the director changes only along the z-axis of the normal to the film. And I parameterize my director as a three-component vector of amplitude equal to 1. So it's very convenient to use cosines and sines, because if you look at this parameterization, so nx is sinus of some angle theta. This is the theta, and its value in the bulk depends on z. There is no y component, and then there is a z component, which is cosine of theta. Why this is convenient? Because if I calculate the n squared, cosine squared plus sinus squared is always 1. So I'm happy about this restriction. Now, the free energy density. You already remember this expression for the free energy density with splay, twist, and bend. So what I'm doing, I'm plugging this in, and I'm calculating what is the density of different deformations for this director field. And how many of you know the expression for the divergence of the vector field? All of you should raise the hands, because it's written on the blackboard, so you can pretend that you know it and just, read it from here. Divergence n is just the sum of the derivatives of the components of the vector with respect to the corresponding coordinate. So it's dnx over dx, and the same for ny. So that's recognizable or not? Okay, very good, because you know you got me being afraid a little bit. So how many of you know the expression for the curl? Okay, it's right there. So all you do, you just calculate the curl and the divergence, and for divergence it's simple. The first component is 0 because nothing depends on x, right? In that direction we have no dependence. There is nothing that depends on y. There is not even a component of the director along y, so it's 0. The only component that survives is sinus theta and the derivative here. So divergence n would give me sinus square d theta dz. You do the same for curl, and then you create the vector product of n and curl n. You realize that this is cosine of square theta, and again the derivative, and if I take the square here, the derivative is squared. So now this is the free energy density. To get the free energy, I have to integrate over the volume, but since the problem is two-dimensionally kind of invariant, I'm integrating only over the z, and I call this per unit area quantity. So now you have this integral. How do I find out the functional, the dependency of theta on z that would minimize this energy? Yes, and the equation is called after. Very good, you know everything, wonderful. So yes, that's exactly what it is. For those who do not recall, the next two slides kind of bring the overview of the variational calculus and how you derive this equation on the left-hand side. So, but the point is that the second derivative of theta with respect to z must be 0. And the solution to this problem is what? Second derivative of something equals 0. Exactly. So this is what's written here. The theta as a function of z is some constant a multiplied by z, linear, plus b. And from the boundary conditions, which are very easy, because I told you how the molecules are oriented here and how they are oriented there, you arrive at the solution that this is the linear function, and as you go from bottom to the top, the angle changes linearly with z. Now you plug this back into the free energy integral, and you get the free energy of these distortions that is quadratic in the difference between the orientation on top and bottom divided by the thickness of the cell of the film. So now this is the home assignment for those of you who don't remember the early Lagrange equation. Now let's make the problem a little bit more complicated. Now the boundary conditions are not rigidly fixed. I should realize that there is some anisotropy in the molecular interactions between, let's say, water and the Lick crystal, but it's not infinitely strong. So if my gradients in the bulk are very strong, then probably the surface tension or surface anchoring will give up and allow me to turn the director a little bit away from the horizontal position. Okay, makes sense if the surface anchoring is finite. So that means that my problem now reduces to the following. In the bulk, I still have the same free energy density expression that depends on the gradient of the depends on the derivative of the angle with respect to the vertical coordinate z. But then at the surface, I introduce the surface anchoring penalty for the deviations of the actual orientation theta naught from the easy direction imposed by the substrate, which I denote with theta naught bar. As I said, it should be some angular, this surface energy should depend on the angle squared, and this is exactly what it is here, squared. And the same thing at the bottom. So I have a different medium, so this is why this W coefficient has a different subscript d. But then I am looking for the same solution. The only difference is now that instead of the boundary conditions that are written simply, theta must be equal theta naught bar, that's it. I have a kind of relaxed condition that the torques coming from the bulk gradients and the torques coming from the surface, from the softness of this anchoring potential, must compensate each other, must be equal to 0. And the bulk solution, of course, is totally the same. And then if you calculate these boundary conditions, you have the two equations here. And it's a simple algebra. I'm not going to go with you through this derivation. You find out that you have theta naught, the actual orientation at the surface, that is somewhat smaller than the theta naught bar that would be there if the surface anchoring were infinitely strong. So the bulk elasticity and the softness of this anchoring potential make this theta naught bar slightly smaller. How much smaller? By this difference in the total orientation at the top and the bottom, divided by the thickness of the cell and multiplied by the L. And L is the shorthand notation for the quantity K over W. Remember, we were talking about the dimensions and the values. It's, as Lisa said, on the order of 1 micrometer. It is true. And now let's just analyze the result. Let's just put this infinite anchoring and finite anchoring side by side and see what's the same and what's different. So what is the same is that in both cases you have a linear dependency of theta on the vertical axis. But then the angles are different. Here I am starting from theta naught bar, and it's fixed. And here I finish at theta bar d, it's fixed. In this case, these two angles are relaxed. Theta at the bottom is smaller than theta here, and theta at the top is larger than theta here. Now, if I will have the graphic presentation of how theta depends on the coordinate z, for the infinite anchoring, I have this line. For the anchoring that is soft, I have the line that is not that steep. The slope is much smaller, and I can extrapolate this dependency away from the cell along the z direction, and this distance is nothing else but the anchoring extrapolation length. This is why we call it the extrapolation length, and someone said already that this is the distance over which the director would relax if it were not for the soft anchoring. But there is something very intriguing if you think more about this. So suppose I'm dealing with this finite anchoring, and this is the free energy of the film. If my thickness d becomes much larger than what it was at the beginning, much larger than L naught and LD, much larger than this anchoring extrapolation length, then I can neglect this L0 or L naught and LD, and my expression will be approaching the expression for the infinitely strong anchoring. So if I make my cell thicker, an amazing thing happens. The surface anchoring takes over. It enslaves the director, because in the thin film, the elasticity of the director wants the director to be not so much perturbed by the surface anchoring. But if the thickness is high, then at the top, I would approach 0. At the bottom, I would approach 90 degrees. So this is the result that to some extent is very counterintuitive. The larger is your system in the nematic crystal, the more important role is being played by the surface anchoring. And it comes from this fact that the elastic deformations energy of the bulk go linearly with the size of the bulk, and the surface, of course, goes as the square. So if you think that this is the end of the story for the hybrid aligned nematic films, do you think so? No, very good. Yes. So it's not, because it turns out if the thicknesses are really, really small, when these gradients are, cranking up, then completely new physics appears. Instead of the uniform nematic director, you have something that is three-dimensionally distorted. It forms stripes, it forms lattices of point defects. And the reason is, again, in our assumption, remember in the picture I showed you that let's assume that the director is in the plane and only changes with respect to the z direction. In fact, it's an assumption, and the real system doesn't care about our assumptions. It behaves just the way it wants to minimize the elastic energy in this case and surface energy. So instead of this thing, the system in this both states prefers to have in-plane distortions. And what does it buy the system? Two things. First, in fact, the divergence of the vector field can be represented in absence of the twist deformations as nothing else but the mean curvature of the surfaces that are perpendicular to the director field. And now you see that in the original assumption, I had only one curvature, R1, and that was it. But if I create in-plane distortions, suddenly I'm bringing in the second curvature, and the sign of that second curvature is not necessarily the same sign as the first curvature. So if R1 and R2 are of opposite signs, remember the soap films on the frames? When R1 and R2 are of opposite signs, that saves you the energy. And you can see it here, that this splay term actually will be decreased if you add additional distortions in the plane of the film. And another thing is that something that we didn't talk about at all, in addition to K1, K2, K3, there are also terms in the free energy density that are proportional to the second derivatives of the director field. And one of those is K24 term. Turns out that the geometrical meaning of this thing is the Gaussian curvature. It's 1 over R1, R2. And this again, if it were in this flat geometry, this thing would be 0. But if I'm creating something like this or something like that, this term is not 0 and it can save some total energy in the system. Yeah, this is the imaginary surface that is perpendicular to the track. And of course, in normal nematic, you don't always can do that. But so this is something to remember, that there is always a danger about your assumptions. And there is also much of the interesting geometry in Lie crystals, even in the simplest case of the hybrid Elan nematic film. So,
Can you say a word of how people measure K24?
read the recent articles. Vincenzo here is co-author a wonderful piece on toroidal nematics. Then there is a recent publication in Physical Review E on the capillary structures. But we measured it in 90s from the observations of these stripe domains.
You do a theory with that K24 and then
Right, exactly. And then we find the period. The period here is, by the way, very large as compared to the thickness of the film. And then we compare what should be expected from the theory and the experimental, match together, reduce the K24, and let other people to verify. So in our experiments, it was like 0.9 of K1, if I'm not mistaken. So there are also some important things to remember. Like you see, I didn't specify because at some level it's obvious. So the values of elastic constants must be positive definite, right? Because if K1 is negative, then the nematic will develop spontaneous deformations trying to make divergence n as huge as possible because it comes with a negative sign in front of it. But when it comes to K24, for example, it's not that simple because K24 is not necessarily obviously positive or negative. You don't know what it is. So you need to do an analysis of the stability of the uniform state of the nematic in order to impose some limitations of K24. And it's called the Ericsson inequalities. And according to them, K24 should be between 0 and, depending on the notations, in the notations that we are using, it's minus 2 K22. So anyway, let's move to the electric field. So it's not only antagonistic boundary conditions that can distort the director, but it's also the electric field. And we know that because we carry all these iPads around. What should be the contribution to the free energy density? Apparently, it cannot be, it should depend on both vectors, n and electric or magnetic field. So if it's two vectors, then most probably it's a scalar product of the two vectors to give me the energy. And well, this guess is again correct. You can check it with the textbooks. This is how you can derive it with the proper sign, negative sign. And this is the probably the last problem that I will consider for today. Again, it's the energy minimization of the ground state of the nematic in the presence of the magnetic field. Let's say magnetic field is oriented vertically. So this is the free energy density. You again parameterize exactly as in the case of the hybrid aligned nematic film. And then you calculate what is the divergence n. You remember it's cosine squared, derivative squared. And then what is the scalar product between the vector b that is vertical and vector n that might be distorted somehow in the xz plane. You obtain this thing. And you write down the Euler Lagrange equation. It's a very nice equation. It says you that there is some characteristic length if you divide the coefficients in front of the two terms. And this characteristic length is inversely proportional to the field and proportional to the elastic constant. And since you have the boundary conditions, and one of those is that at the boundaries, the director continues to be in the same state as before the magnetic field was applied, you arrive at the conclusion that the first non-trivial solution in the form theta equals some coefficient and some function of z would occur when the magnetic field overcomes the elastic resistance, when the magnetic field is higher than some threshold value that is inversely proportional to the thickness of the cell and proportional to the square root of k and inverse diamagnetic anisotropy. And so this is, in essence, all that you need to know about the physics of displays. When the optic axis changes because of the applied electric field, the optical appearance of the pixel changes, and that's it. So, but the last thing, just to finish with a nice picture, is if you consider the Frederiks effect in this heliconical state, then what happens is that you're controlling the pitch of your twistband structure with the electric field. Depending on the value of the electric field, the spring kind of stretches or shrinks. And because of that, the Bragg conditions change. And because of that, you have colors of reflected light changing nicely. And in this particular case, you don't see it, but it changes from ultraviolet, that's why you don't see it, to the visible, that's where you see it, and then to infrared, when you again don't see it because it's black. So it's a kind of interesting thing that you can control the color of the cholesteric crystal by the electric field. That's it for today. Thank you very much. Yeah.
So this color tuning is possibly has application in display. Yeah, but given that people now use LED displays, how is it?
No, the LED displays are only a fraction of the market. LED, most of the time, are used as the backlight for the liquid crystal display. But for marketing reasons, these devices are still called LED displays, when in fact they are not. They're LCDs because the LCD controls the transmittance. The LED just provides the background